Hello everyone, thank you for joining. Today we're going to solve a question on from Cambridge entrance paper, maths entrance paper. So we are given a function where a and b are positive numbers. Well, I'm assuming a and b to be a real number. Right, and the first thing we need to do is to find the stationary points, and then we need to show that this forms some the values forms geometric progression, and then we need to give a rough sketch. So if you'd like to try it first, pause the video, and then we could go over it together. Right. So let's go step by step then. Find the stationary points. Well, we know f dashed of x is 0, so we have a e to the ax cos bx minus, it will be minus because when we differentiate cos we will get sine, so it will be b ea to the x sine bx is 0, factorizing ea to the x into a cos bx minus b sine bx is equal to 0. Well, e to the a x is not 0. That implies a cos bx minus b sine bx is 0, or we could say a cos bx must equal to b sine bx. And then that implies that we have a over b is equal to sine bx over cos bx. Of course, it's always troublesome to divide anything by a trigonometric function, since if you consider cosine will have so many singularities, so many zeros, which means when we're doing this division, we're saying cos bx cannot equal 90 degrees, 270 degrees, and so on. Yeah. But the good thing is, none of these values are a solution to this equation, so we can do the division with no problems, right? So we have tan bx is equal to a over b. That implies bx is equal to tan inverse of a over b. But since tan repeats itself every 180 degrees or every pi, so if we have a solution there, that means we will have another solution and then another solution if you take pi steps. In other words, we can write bx is equal to tan inverse of a over b plus pi n, where n is an integer. A better notation, I should have said bxn, right? So in other words, we have xn is equal to 1 over b tan inverse of a over b plus pi over b n. So that answers the first question, right? And the second part of the question says that show that the values of f at the stationary points with x is greater than 0 form a geometric progression with the common ratio and so on. So let's simply follow the instructions. They are saying show that, and we care about the function f and the stationary points x and. So what we are interested in, well, first of all, to show something is geometric progression, all we need is we have ar squared, and so on. So if we have any term, any consecutive terms, let's say Sn plus 1 over Sn, that should give us r. Just like, ar over second term divided by the first term is r, or if you have ar squared divided by ar, you always get r, which is a common ratio. In other words, we want a function f of xn plus 1 divided by f of xn to equal common ratio, and which would turn out to be this, according to the question. So all we have to do is we have to plug that in there, and then hopefully get the answer. So let's do that, shall we? Just to recap that, f of x is equal to e to the ax cos bx, and we have xn is equal to tan inverse, 1 over b tan inverse a over b plus pi over bn. Okay, so, and we want f of xn plus 1 divided by f of xn, which gives us e to the a xn plus 1 cos b xn plus 1, right, divided by e to the a xn times cos b xn, right. That's equal to e to the a 1 over b tan inverse of a over b plus pi over b n plus 1. We're looking at the n plus first term, times cosine of b xn, which is 1 over b tan inverse of a over b, plus pi over b n plus 1, right? And we want to divide this by e to the a 1 over b tan inverse of a over b plus pi n over b, because this is the nth term, times cos b into 1 over b tan inverse of a over b plus pi over b n, right? Okay, right. Now let's simplify. To simplify, well, let's simplify these two exponentials first. So let me put them in a circle like that. Okay, so we have e to the a over b tan inverse of a over b plus a pi over b n plus 1. And we're dividing that by e to the, because this division, simply say minus a over b tan inverse of a over b plus a pi n. It should be minus because it's in the denominator. So a pi over n over b, right? So there should be brackets here. Okay. So let's simplify that. Now, one thing to notice is that this will go with that. Well, let's not cancel the e's, but the powers will go, yeah? So we will have e to the a over b tan inverse of a over b, and we will have minus a over b tan inverse of a over b. This is the same thing. And then times e to the a pi over b n plus 1 minus a pi over b n, right? So this will give us e to the 0, which is 1. We can simply forget about it. And then we have e to the a pi over b n times, that would be plus a pi over b, and then minus a pi over b n, right? Which would give us e to the a pi over b, because this will cancel with that. Okay, so if we simplify the exponential here, that gives us that, which is very close to the answer. So, because I think it was showed that e to the minus, yeah, so same thing, just minus. So we're hoping that this complicated expression here will give us minus 1. That would solve the problem, yeah. Okay, so let's have a look at now, let's have a look at the cosine, and let's try to simplify this. So what would that give us? Right, so let's expand, and we get cos b, excuse me, we will have cos b over b. So the b will cancel with that one and that. And similarly here, the b will go. So what we have is we have cos tan inverse of a over b plus pi n plus 1 divided by cos tan inverse of a over b plus pi n. Okay, so Right. Okay, so let's use the expansion. So let's expand this using the expansion of cos A plus cos B. So we have cos A plus B, is equal to cos A cos B minus sin A sin B, right? So we have cos tan inverse of A over B times cos pi n plus 1. That's cos A cos B, and then we have minus sine tan inverse of A over B times sine pi n plus 1, right? And that's divided by cos tan inverse of A over B times cos pi n minus sine tan inverse of A over B times sine pi n. Now let's think about sine. So sine pi, let's have a look at this. We're looking at sine 0, sine pi, sine 2 pi, and so on. Whatever the n is, since n is a positive integer, or it doesn't have to be positive since it's an integer, this will always give us 0. And this will also give us 0 as well, isn't it? Because you just get either pi or 2 pi, 3 pi, and so on. So it boils down to only the cosines on the left-hand side, and we can simply cancel that with that. So the only thing we're left with is cos pi n plus 1 over cos pi n. And that will clearly give us minus 1, isn't it? If you want to do it explicitly, so we have cos pi n plus pi here, and here we have cos pi n. Again, if we use the expansion there, we'll have cos pi n times cos pi minus sine pi n times sine pi divided by cos pi n. So this is 0, sine pi is 0, right? Cos pi is minus 1. So this is minus 1. And then that goes with that. So the answer is indeed minus 1. So it turns out that the ratio turns out to be e to the a pi over b times minus 1. That's simply e to the minus e to the a pi over b, friends. Yeah, and this is, I think, what we were supposed to show. Yes, that's what we were supposed to show. Okay, now given a rough sketch to that function, well, since a is positive and b is positive, we will have some like the resonance, if you're familiar with the resonance, the graph, because what's going to happen is we have some, to understand, let's make a is a1 and b1. So what we will be looking at is we'll be looking at something. So this is x, this is f of x. So cosine, if b is 1, f of x is simply e to the x cos x. So you have something like, this is our cosine function. It will just be oscillating as usual. And the exponential, e to the x will look like this, going through 1, okay? And if you multiply the both, you'll just have some oscillations going like that, and it's getting bigger and bigger, and so on. Yeah. So it's not going to, these are not going to be symmetric. It will probably be more steep on this side here, because the function is increasing exponentially. So you would probably get more something like steeper on this side, but it doesn't matter. It's a rough sketch, so you'll have something like this, right? Okay. Well, Yeah, so I think this was a nice question. If you think about it, it required nothing more than A-level maths knowledge. It's just differentiation, product rule, and some geometric progression and sketching graphs. Yeah, okay. Well, I hope you enjoyed it. I hope you found it interesting. Thank you for joining, and I look forward to seeing you in my future videos. Thank you.